B1, which is in the room, just go across the posters, and there is a room there. So yeah, you may prefer to be there or here, whatever you want. Here we are going to have 5 talks. We will start with 2 talks by Professor Masoud about nuclear ammonia and then hydrogen. Then we will switch to Oriol about multi-energy grids. Then there is this talk by Jergeli about this survey on solar energy. And finally, there should be a talk about wind turbines by Kalautit, which I don't think he's here right now, but hhopefully he will be here by the time his talk should start. So each talk should be like 15 minutes. We're expected to have some time for questions, so I will ask the speakers just to talk for 10-12 minutes. I will raise a signal when you are getting there. And yeah, just have fun and ask any questions at the end. We should have a microphone there, so if you have questions, just raise your hand at the end of the presentations. Yeah, just Professor Masoud, you can start.
Thank you. Thank you very much, gentlemen. Today we'll talk about nuclear ammonia as a renewable energy source and an innovative approach to advancing sustainable fuel solution for the global energy crisis. Okay, so the first here, the paper thoroughly addressed different operational challenges of the renewable energy and ensuring the safe framework and how the system can be adopted. So the introduction, expanding population, as you know, the demand of the energy is increasing because we have a growing economy and a growing population all over the world. It's and the carbon emission growing rate faster, the population stack reflections, the alarming trending underscore the urgent need of the actions, US economy activities, including accumulating the huge balance of payment and the other deficits and etc. that need a huge amount of energy. So if you can see here, why energy is important. If you have seen the global warming here in the first map, early 1750, 1800, 1850, 1950, and 2000, the world population and sea emissions, and you can also see the US oil reservoir and the oil imports. And on the bottom here, you can also see here the trend of 1973 to 2023, the change of the global warming temperatures, and now we are reach almost 400 degrees Celsius over here. That's very critical. So the problematic area fuel, the significant portion of the energy needs to be met by the fossil fuel, the major part of the also then, and the renewable energy sources including geothermal, fuel cells, hydrogen, green energy, hydrogen nuclear energy, wind power, and biofuels, etc. Over the past 3-4 decades, the industry has played a significant role in meeting the energy need. It has been introduced technologies such as the coal flux and fluidized bed and extra having sulfide contents and saturations and CO2. However, these solutions are not without their drawbacks. Okay, the problematic area over here, if you can see here, the operation here, we have a different here, the electrical imports here, the hydro here, the bypass here, and over the energy delivery here, the use of the energy 35.2 here, and the loss of energy 56.8 here, the electrification and the losses here. If you can see the huge losses here, the residential, commercial area, natural, this is the energy users in the United States of America here. So next here, what is ammonia basically? The ammonia imports around 2/3 of its petroleum, totaling 200 billion gallons out of 290 billion gallons. And with that, majority of the petroleum is consumed for the transportation, making imperative and they develop the viable needs. This situation critical and disruptions, they could severe consequences of our society, optimism, and the green future sustainable that is could not be possible without a sufficient energy need. Okay, how the energy here, there is how it's processing here. There's the natural gases here, desulfurization ammonia plant here. Then we have a primary and secondary farmer, the processing, the primary farmer, secondary farmer here. air the nitrogen, and then we have a shift converter processing, CO2 removal, methanizations, ammonia synthesis, and refrigeration, and this, the other section which we have used a different form of ammonia, that is ammonia storage, ammonia bulk storage, and the different uses of the, we have the CO2 synthesis, and we can also use at the urea ammonia plant, etc. So the steam methane deformant specific hazards, so that is safety, the first here, the complete combustion, the over here we can see here the good combustions here, that is the combustion system at time, temperature, and turbulence here. The complete combustion system, incomplete, if you have complete combustion, certainly we have a complete combustion. When it's carried out, you will produce a carbon dioxide, hydrogen. Over here, the complete NOx and SOx will be emission control here. When you have an incomplete combustion, you have a huge amount of the carbon monoxide, and certainly you have carbon dioxide. That is more hazardous than the NOx and SOx. That's important to have, and you can have a maximum energy conversion in the combustion system here, in the combustion product here. That is the other impact during the ammonia processing. So ammonia as a fuel here, if you can see here, the first year it was used, ammonia powered a pickup at 2007, that is Michigan University have developed the car here, then the ammonia powered a pickup 1933, then the altitude records burning ammonia, the helicopter ammonia powered motor bus in 1943, that's also utilized in the past year. So this ammonia electrolysis here, the ammonia, when we produce the ammonia electrolysis process here, how we ammonia produced here, that is the process here, the ammonia hydrogen oxides, that is ammonia oxidation, and the cathode water here, and that's the economic factors. So over here, the next stage, the cathode water reductions, ammonia, the other reactions, economic needs, and the reaction will take place, and we produced here the energy sources here. And here, if you can see the hydrogen and ammonia actually produced in the electrolysis process here. So at 25 degrees C, what would be here? The theoretically 1.5 to watt hour per the hydrogen consumption, the average cost with the ammonia $175 per ton here, and then the solar energy is 0.21 kilowatt per hour, that is a comparative analysis. So the hydrogen cost is 0.92 kilogram per hydrogen that will be produced in economic analysis if we are the 25 degrees Celsius. So that is DO, the DO rate, the Department of Energy, using the solar energy. You can see the first instance here, the energy produced, the hydrogen cost here, the water electrolysis 33, and over here we use 7.1, and ammonia electrolysis 1.5 and 0.83, that is cost of the hydrogen cost here. So then 95.3% lower energy and 87% the charger at the saving of the 95.3 energy is saved by using the electrolysis process here. So here, the minimized hydrogen storage problem, zero hazardous emissions, fuel flexibility, low temperature operation, fertilizer plants and municipal water waste, the treatment stations could be potentially produce their own energy from the waste system here. So we can also install the different type of the projects here, that is the, over here, that is the energy here, the clean energy ammonia electrolysis for the production of the hydrogen. You have ammonia with the water here, the wastewater system, the hydrogen produced, and clean energy, so the energy we can produce on both sides here. So use as the power source here, the ammonia in the SOT, the generators are the different form of the energy we can use here and produce the operation day theoretical conditions here. So that is different form here. So the fuel cells are the nitrogen and electrolysis energy here, and the conclusion is where develops the waste of the ammonia as a sustainable fuels, exploring the use of the fuel energy, consumption, economics, with hydrogen production, advancing the greenhouse, and the topics underscore the ammonia promises the scalable, with versatile quality, and can produce a more cost-effective manners. Okay, so that's, thank you, and now, if you have any question.
Okay, anyone has any questions here? It was very, very fast. Thanks a lot for being on time. Yeah. So, no questions? Okay, I have a very short question because both in your presentation and when reading the paper, it was like, oh, everything is wonderful with ammonia. So are there any drawbacks? Are there any problems with?
Yeah, every challenge creates the opportunities.
Sorry?
Challenges create the opportunities.
Okay.
So there is a lot of challenges, in particular to store the ammonia.
Okay.
It's very difficult to storage of the ammonia. You have to drop the temperatures substitute in order to, and that's the biggest challenge. And then bring back into the evaporation condition of the liquid form, then to carry that is another challenge. So there is a multiple opportunity which we need to do a more search in order to address these challenges.
Okay.
And it's most important, it's a cheaper. It's a cost effective. Mean you can take the oxygen, you can take the nitrogen, and only you need hydrogen. And with you process through the methane gas and make the ammonia, and it is clean and neat energy. You can run the tractor, you can trawler, anything you can use it. But the question is that, of course, storage and import, export is more important.
Okay, that's great.
Okay.
So, any other questions here? If not, we will just go ahead, and it is still Professor Masood.
Good. Next. Okay. No, in my last presentation, we have a completely focus on the ammonia productions. Certainly, for the ammonia, you also need a hydrogen to process to complete combustion, nitrogen and hydrogen in order to make the ammonia that is lost in presentation discussed. Now, question is that if we advance how sustain we can produce the hydrogen in cost-effective manner. Is that clear? Mean you have hydrogen, but you don't have a nitrogen. To complete a process, primary secondary formula, you make the ammonia by nitrogen and processing chemical reactions. Now, question is that how much it would cost you to take the hydrogen. You have the nitrogen in the atmosphere, where you use it and take the hydrogen to process and make the ammonia. And to making a hydrogen is not a cheaper, it's expensive. So that's, in this slide, we will talk about advanced sustainable hydrogen production. How expensive and how... Okay.
This is because we are streaming this live on
Okay. I should be sticky here. Okay. No, in my earlier slide, we have discussed to process the ammonia to produce the energy. Now, over here, how we can produce hydrogen with cost-effective manner. We have two processes to reduce or to make a minimum cost in order to produce sustainable, reliable hydrogen production in order to complete the process here. Okay. No, the hydrogen production methods are different. We use the catalytic process, a different process we used here to produce the hydrogen. We have used hydrogen for the vehicle and directly in the hydrogen, green hydrogen, gray hydrogen, and blue hydrogen, different form of the hydrogen we used. And we also use the hydrogen to make the ammonia in order to use another form of fuel to put in the liquid form to have the different form of the process here. So the biggest challenge, how much it would cost. You have the methane gas, you got the methane gas. Now, methane gas has different stages. The first stage is a primary reformer. The second stage is secondary reformer, converter, shift converter, reactor, and then synthesis gas to produce it. No question that each stage need a processing time, need a cost effectively. So now we will talk about how it can do it. So here, if you can see here, SMR, that is a methane processing, that is a primary secondary reformer, and biomass hydrogen productions. In methane gas, ICH4, it contains 70 to 90% here. The ethane, propane and butane is a small amount, carbon dioxide, carbon oxygen, 0.2%, nitrogen, 5%, and hydrogen sulfide, hydrogen H2S, that is a 5%, and the other gases, argon, helium, nitrogen, that is at few traces in the fuel or the gas which we got from the system here. Okay. Now the first here, if you can see the SMR and steaming process here, so I got here the first performed here, I got the oxygen here, and preformed a natural gas zone here, carried out the combustion system. I have a CH4 methane, a plus oxygen, and now I can make carbon monoxide and H2O. Okay, content over here, the first zone on this area. In the second zone, when it's processing thermal and catalytic zone, I have CH4 plus water content. This is the water processing, and I made the carbon monoxide and hydrogen. And the next level, carbon monoxide plus hydrogen, complete process, and I got carbon dioxide and hydrogen. This is which I need to produce in order to make the ammonia. Okay. Now this carbon, I use a different form of absorber to absorb the carbon monoxide. So this is the hydrogen which I need to do the different process. That is synthesis gas which contain hydrogen and carbon dioxide. Okay. In the process here, if you can see here, the different form of here, the different pressure, diabatic compression works, final, the pressure, hydrogen, and methane. If you can see here, this is my pressure from 0 to 90 here, and that is a compression energy mg per kilo, how much I need. So if I compress the here, so it will produce here. So remember, to convert ammonia into the liquid form, you need a high compression ratio to convert into the liquid form. So over here, then we can transport here different form here, and this is the different line, the cryogenic tank, the tubular tank, because it's another difficult challenge to transport the ammonia or hydrogen in the different forms. So we have different forms here. So if you can see the cryogenic tank over here, and this line is a pipeline. When you turn into the liquid form, you can transmit as far as you can, it's possible. And then you have a tube trail, the other form, that is a 1.5 here. And over here, I can go up to 4 if I had changed into the liquid form. Okay. So in the SMR hydrogen production cost here, if you can see the facilities, the large facility 1.3 and over here 25.3, small. And this is the different processing plants we have used here. Spec ESIG, how much dollar per gigajoule energy you need to consume here. And that is the cost, $1 per gigajoule energy will cause you to change the gas into the liquid form in order for the transportation purposes. That is the first SMR hydrogen production cost. And the second here, the biomass per hydrogen production cost here, they have used the facility here, the different form of the facility, and biomass, that is the references, different form. The plants here we have used here, and hydrogen price $1 per gigajoules here, 10.0 here, and over here 17 point here. And that's the biomass pyrolysis, that is the arm form, and this is the biofuel gasification. Two form of the biomass is gasification and pyrolysis, two forms we have used, and it would cost it. If you can do the comparative analysis here, so the biomass price, it can go 16.5 man 1995 and over 46.3, that is if you use Larsen 92, that is 2.2 gasification here, and the pyrolysis, and that's the product over here. So if we can go back here, so this is a maximum 11.2 with the SMR hydrogen production. That it's been, it has a lower cost than if we use the pyrolysis or a biomass hydrogen conversion here. Okay, so that is the SMR, the process here, the SMR that is critical. The first the compression ratio of the compressed here, we use the primary form reactor here, and that is the processing and the compression here, and the liquid form, the different form of the tanker we have used methane gas, and processing here we have the liquid form do further processing here. So over here, the SMR process and chemical reaction, the first reactions will take place 2.6, that the first, the hydrogen will come to the kilojoule per moles here, the first reaction, the secondary form, primary form conversion here, and that is methane gas and further processing, and the last stage here, we have the over here we have a maximum carbon monoxide, and this is the area which we have produced a 75% hydrogen which we need in order to processing a different form of energy here. So again, this is, we need a balanced combustions. This is by balanced combustion here, the complete combustion. You have the carbon dioxide here, the complete combustion. NOx and SOx will be emission control here, the minimum. And over here you have the carbon dioxide that is incomplete combustion. So that is not preferable as far as the hydrogen production is concerned. Over here, the complete combustion or balanced combustion system will take 3 T's for the good: temperature, time, temperature, and turbulence. That's critical over here. In the combustion system, so it's incomplete mean you don't produce a carbon dioxide. You have a carbon monoxide that is more dangerous compared to the other gases here, and it produced more NOx and SOx. That's greenhouse gas emission control here. So then another biggest challenge here in the tube skips, when you have the high temperature 800 degrees Celsius, the primary reformer, secondary reformer, we have 800 and 900 degrees Celsius during methane gas cracking process. And that is again very critical. We need to work on the tube crackings because of when you have the high temperature here, it will do the primary, secondary, and tertiary. That's a different form. So normally we operate at this area. We won't go this side because it exposure of the time and maintain the temperature less than 800 degrees Celsius during the crossing gas, CH4 gas with the hydrogen. So that is the hydrogen production method. Different from the significance, 90% global energy we use for the SMR processing and enhanced gasification pyrolysis. It's expensive, but again, it's a reductions, and it will also help to greenhouse gases reduction as well. So the law safely, sustainable, and the more implemented here, this study will also reduce the operation, the dynamic assembly perform more effective, and NOx and SOx you have reduced at a minimum and have maximum energy conversion as far as the SMR, pyrolysis, and biomass energy is concerned. That's it from my last slide here. So do you have any question about the pyrolysis, SMR, or biomass? So I'm ready to answer your questions here.
Yeah, so any questions? No? Okay, so I have a question.
Yeah, yes.
So just 2-3 weeks ago, I was talking with a colleague, and he told me, yeah, we had some small experimental hydrogen production plant, and we just stopped doing that because it was very difficult to transport, to get the hydrogen from there to some other place to use it. So what will be your advice for, because in a place like this, in the Canary Islands, we don't have pipelines. We are not going to lay pipelines. So what?
The hydrogen is the biggest challenge to transport. The hydrogen has a high diffusion power. Did you know diffusion energy? I mean, if you put in the stainless steel, it will diffuse from the stainless steel immediately. So that is the biggest challenge to store the hydrogen. What we do, we processing hydrogen with the nitrogen to converting a blue ammonia or gray. Basically, it's a form of liquid to process it.
Okay.
So the clean and neat, then we need to convert in form of methanol. That is another form of the hydrogen. So it will turn into the liquid. Until it won't change into the liquid, you cannot carry, you cannot transport. To change into liquid, you need to change into the methanol form or you need to change into the ammonia form. Clear hydrogen you put in the pipeline, and after you check, there's no ammonia, no hydrogen. It escaped from the pipeline. Okay. It has the highest diffusion power. It passed through the pipeline. Okay.
So no questions? Okay, if that is the case, thanks, Professor Masood, for your talk.
Thank you.
And it is now Oriol's turn, I think. And we will hear about this software for stability analysis. And yeah, just.
I put my presentation first. Sí, yo es lo que les he dicho a ellos, digo, ¿en qué momento? Vale, perfecto.
Adelante, atrás y
¿El puntero?
El puntero no se ve, o sea que
vale.
Se ve muy poco.
Ah, vale.
Okay.
Well, hello everyone. My name is Oriol Cartiel, and I will present our work titled An Innovative Software for Stability Analysis of Multi-Energy Grids. This research has been developed at UPC in Barcelona under the supervision of Luis Sainz and Juan José Mesas. Today, we will go through the 5 key sections outlined in this index. To address climate crisis, clean resources and energy efficiency are crucial. Renewable technologies like solar PV and wind power, along with HVDC links, have already been widely integrated. In this context, multi-energy systems are emerging as promising solutions, offering flexible energy storage and management to deal with the variable and unpredictable nature of renewables. However, these new infrastructures also introduce significant challenges, particularly small signal stability issues caused by complex interactions between power electronics and traditional grid elements. Why is a new tool needed? It can be said that there is a lack of tools capable of effectively analyzing small signal stability issues of multi-energy grids, particularly when dealing with large-scale systems and black box models. Traditional approaches, for example, in my research area, each have their limitations. For example, frequency scans detect resonances but don't provide effective solutions. Model analysis is computationally intensive, and time-domain simulations become impractical for large-scale multi-energy grids with black box models. This highlights the need for new tools that are capable of effectively analyzing this type of problems, which also supports black box models and provide some damping solutions that we will see later. So here, to address these challenges, we develop an innovative software for stability analysis. It tackles computational limitations while maintaining accuracy. It simplifies the stability assessment with a user-friendly stability criterion. It supports black box models. It calculates participation factors to locate critical components. It quantifies system stability using a known damping margin indicator, and also propose some damping solutions, and most importantly, it scales efficiently even to very large grids. So now we move forward to the software itself. Based on agreed data of an M-bus system, using either white box or black box models of each of all the grid elements, the software follows a 5-step structure to efficient stability assessment. Let's go briefly now to each of these steps. The first step focuses on the construction of the nodal admittance matrix, which is the core of the methodology. It is built using the voltage node method and supports both white box and black box modeling, making it versatile for real-world applications. This approach represents a unified system representation and making it really versatile. Once the nodal admittance matrix is constructed, the next step is to identify resonances using the resonance mode analysis. This consists on the eigenvalue decomposition of the nodal admittance matrix to identify critical resonance modes and evaluate model impedance peaks across a frequency range. We are also capable of calculating participation factors to locate, which are based on the eigenvectors of these critical resonance modes, to locate the most affected buses or the most critical components. To improve computational performance, the software uses two different strategies based on the sparsity level of the nodal admittance matrix. We have the faster resonance mode analysis for small grids and the Lanczos-based resonance mode analysis for large and sparse scenarios. Now we are going to start seeing an example for clarity. This is based on the IEEE 3-bus system, and here in the slide, the view of the slide shows the resonance mode analysis results of this 3-bus grid. Here we can see the 3 individual modes of the system, which are labeled as ZM1, ZM2, and ZM3. And highlighted in bold, we have the envelope curve that represents the critical mode of the system. This critical mode of the system is the one tracked by both faster and Lanczos resonance mode analysis approaches. Just to end this slide, I want to say that resonance frequencies are located in the peak values of this curve. So in this example, as you can see, we have 3 resonance frequencies. Now, when we have the resonance mode analysis results, the next step is to assess stability. The third step focuses on applying the positive mode damping stability criterion. The criterion is really, really simple. You will see it now, okay? This criterion says that the system is stable if at each resonance frequency, the ratio or product, what matters here is the sign of the result, okay? So what I was saying is that the ratio or product of the real part of the critical mode and the slope of its imaginary part must be negative. This means that the mode is damp. Following our IEEE example, okay, now here, as you can see, we include at bus 2 a BSC connected via a transformer. Positive mode damping criterion results shows that the system is unstable at 1.25 kilohertz, since both the real part, the blue curve, and the slope of the imaginary part, both are negative, so negative, negative, positive. This means that we have an undamped oscillation. Also, participation factors points to bus 4 as the most affected bus in this instability, where the BSC is connected, obviously. And time domain simulation confirmed the predicted 1.25 system instability. After applying the positive mode damping criterion, the next question is, how stable is the system? Imagine a metric that quantifies this in electrical terms, something that tells you exactly how much damping you need to include in terms of conductance or resistance and where to apply it. That's what our damping margin indicator does. It tells you how much conductance must be added at a specific bus to improve stability. And as you can imagine, as we have everything in electrical terms, this not only gives you a numerical measure of how stable the system is, also provides a direct input for compensator design. Now, once stability is identified and quantified, the next step is to propose some damping solutions. The software proposes two different strategies. We have active compensators, which modifies the equivalent admittance of the BSC via a feed-forward filter in the current loop, as you can see here in the image. And also, we have passive compensators, which are implemented using a shunt RLC filter connected directly to the affected bus. Additionally, to improve stability, the damping compensators were designed using a bandpass filter-based admittance. Its key design condition is that at the resonance frequency, the damping compensator must be at least equal to the damping required calculated with our damping margin indicator. The filter also is centered at the resonance frequency, and the Q factor is designed based on our damping objective, as you can see here in an example. Ending with our example, IEEE 3-bus example, implementing an active or passive compensator at the most affected bus, which was bus 4. System stability is restored as time domain simulations confirms. Moving forward, based on our experience to improve computational techniques, we propose, and the software uses, two different computational techniques. First, we have sparse matrix techniques which take advantage of the fact that large admittance matrices contain mostly 0 elements. This speeds up, reduces memory usage and speeds up computation. Second, parallel computation accelerates the eigenvalue decomposition across the entire frequency range that sometimes it's really large. The combined effect of both results in a robust and scalable tool that makes really versatile for real-world application with grids with, for example, tens of thousands of buses. In our paper, we performed two different stability tests. The first one is based on an ICDC multi-energy grid with which includes a black box model of a hydrogen subsystem. The software identifies system stability at 0, 1.6, as the criterion is not matched here. Participation factors points to bus 5 as the most affected bus, where the hydrogen subsystem is connected. And thanks with the help of the software, we design a passive damping compensator and system stability is restored. The second test involves a large-scale system which is based on a 70,000 bus supergrid. System stability is assessed. Two critical resonance modes are identified at 1.04 and 1.07, which not match the stability criteria. Two active compensators are designed and implemented in their own buses. But here what I want to show and what's remarkable is that the entire system analysis, which involves an admittance matrix of 140,000 dimensions, was solved in just around 9 minutes. And to end, I want to highlight that this software bridges the gap between theoretical complexity and practical usability, bringing a small signal stability assessment closer to engineers and researchers. Its key strengths include being a robust and scalable tool well-suited for multi-energy grids with high penetration of power electronics. It combines the positive mode damping criterion with an optimized resonance mode analysis approach. It delivers practical solutions, as we saw, of damping margin indicator and damping compensators. It supports black box models and was validated on systems ranging from a simple 3-bus grid to a synthetic 70,000 bus supergrid. And as shown on the slide, as you can see, full stability analysis can be completed in a matter of minutes, even in really large grids. Thank you very much for your attention. I'm now open to any questions you may have.
Thank you. Are there any questions in the room? No? Yeah, please go ahead. We have a mic here.
Okay, so now about the first questions, if I move back. As you can see here, I test even to a 70,000 bus grid. It's because I didn't find anything bigger and anything that supports more. But I guess that it can be the limit. There is no limit. For example, well, the limit is in the computer and for example, the RAM memory that enables the saving memory. I don't know how to say the memory usage that you have available in your computer. But using our techniques, for example, the sparse matrix techniques and parallel computations, this helps you a lot because as the grid increases, as you can see here in the sparsity level, for example, a 70,000 bus grid, the sparsity level is 99.995. This means that this percentage is the amount of 0 elements that we have in our admittance matrix. So as larger the grid is, larger will be the sparsity. So I think that using sparse matrix techniques, it not limits the usefulness of the tool. And about the second question, if I go back, you will see now, it's how to include other vectors. The answer is really simple. If you have the admittance model of that vector, of a hydrogen system, of a natural gas system, if you have the admittance, you can include it using the voltage node method. It's really simple than that. So there is no limitations.
just a very quick one. Are you planning to release this, to put this somewhere in GitHub or something like that, or it's going to be closed and just for you?
No, my plan, well, this is part of my PhD thesis that I'm now working on it. And my plan is to provide everything in open access and publish everything in GitHub or any platform on internet, but all available for everyone who wants. As each of these steps are one paper. So this is a compendium of articles that in a unified software. But all will be available, yeah.
Okay, that's great. Thanks a lot.
Thank you.
Now our next speaker is from Bulgaria, I think. Hungary, sorry. So yeah, so this survey on PV use on Hungary. And yeah, I think just a quick check. I think Kalautit is here for the, yeah, okay. And your talk is already here in the computer. Okay, thanks. So, please.
Thank you very much. Hello everyone, good afternoon. My name is Laszlo Gergely. I'm from the Budapest University of Technology and Economics. And my core research area is the load matching of solar PV generation on basically rooftops and the consumption it. So basically the simultaneity of production and consumption on site with households with PV. However, we've done numerous simulations of what the self-consumption these households can be and how it affects the national electricity markets, grids, etc. But we face challenges on the validation of local consumption, self-consumption. Why so? I'm going to introduce you into the topic in the next few minutes. So a bit about Hungary, how our power plant portfolio comes from. Mostly, we have power generation from nuclear power plant in Hungary. However, regarding the built-in capacity of power plants, major capacities come from solar. PVs above 50 kilowatt amperes, below some. Specifically, we call this household scale power plants, HSPPs, short. We also have pretty much of gas, mainly for balancing purposes at the moment, and we have some of the waste, minimum of water as well. So when we look at the built-in capacity, at the moment, by the end of 2024, Hungary had the 8th largest watt per capita built-in capacity, approximately and getting up to 1,000 watts per capita at the moment. From the perspective of the number of installed plants, we have approximately 300,000 installed plants with HSPPs, so household power plants. That adds up to 2.7 gigawatts of installed capacities out of the 7.7 gigawatts of PV capacities in Hungary. And mentioning that it's approximately 300,000, you could have calculated that roughly an HSPP comes with a capacity of 9 kilowatt peaks. The utilization factor of these are approximately 10 to 13% in Hungary. Now a bit to the household's consumption. So that's all the information we know on the production side, and we also know the exports from these plants. But we also want to know the consumption of these households to clarify on-site consumption of these households. How does the consumption of the households decompose? The overall electric consumption of households at the end of 2023 was 12 terawatt hours, mostly appliances in the households and lightnings. However, major part came from domestic hot water because in Hungary a lot of electric water heaters are installed. And there is an increasing trend in residential heating sector with electricity and cooling with heat pumps in the sector. As you can see, there's a major increase in the recent years compared to a baseline to 2015. There's 4 times as much electricity consumption of households heating and approximately 3.5 times consumption of cooling in the sector. Overall, the electricity consumption of households is increased by 16% in the recent decade. However, we have no specific knowledge on this data. These are basically simulational data as well from the National Statistical Office based on methods of heating degree days and cooling degree days calculation. As I guess in most of the countries, these specific consumptions are not separately measured because it wouldn't make sense. So basically, we want to clarify situation on this a bit more. Why so? Because in Hungary, as I guess in many countries, we only have 1 meter for electricity billing. That is a bidirectional meter, and this only measures electricity interaction with the grid. So the part of the photovoltaic generation that's injected back to the grid or that's withdrawn from the grid. However, there's a major part of electricity consumption of households with photovoltaic plants that are consumed on site from the photovoltaic system. On the figure below, you can find these as export with the yellow one, the import, so the withdrawn from the grid with the blue one, and the on-site utilization of the power plant is obviously this green area, what we cannot measure because it's behind the bidirectional meter I mentioned. So basically, we want to clarify situation on this, as well as having a bit more detailed information of the consumption of the specific appliances in the households. As we don't have separate meters, we had to take another method of knowing this, and for that reason we constructed a questionnaire survey that we conducted in the residential sector in Hungary. So the main objectives were to justify that the national PV systems are sized as we believe. In Hungary, there's a net metering system, so we believe that the photovoltaic system sizing is putting the size of PV system on the rooftop that covers the annual demand, electricity demand of the household. So that was our first goal. The second one was clarifying the orientation of these systems because there's no database on the tilt angle or the azimuth angle of these systems. That could be crucial, for example, TSOs and DSOs. And we also wanted to quantify the consumption behind the meter and the typical consumer appliances we find at these households with household-scale power plants. And the results of the query. At the moment, the query is non-representative. However, we have enough feelings to have some insights into the results. Many of the results are not game-changing, that's what we anticipated, but there are some interesting facts in the results. First of all, the orientation of the PV systems comes as expected. Most of the PV systems are oriented with a tilt of 30 degrees. That's the optimal in Hungary from the perspective of annual yield. However, there is a major part with a tilt tending towards 45 degrees of tilt angle. That's because of the metering system and metering scheme. And in Hungary, because of the building system, basically it was worthy to everyone who could to install such systems. So systems got on rooftops with, let's say, not with the optimal tilt angle of the systems. Regarding the azimuth angle of the systems, you can find that mostly systems are oriented towards south, as one would expect. However, there is major contribution from southwest and southeast as well. And I mentioned this could be useful from checking data of the TSOs. TSOs are now buying data from some separate systems across the country, and these data with some simulational efforts could be cross-validated with the TSO inquired data on this. Second, what's the overall consumption of the households with HSPPs? Well, because of the behind-the-meter additions that we found out from the survey, we concluded that this is approximately 7,000, more specifically 6,900 kilowatt hours per year, which is much more significant than the national average of 2,500 kilowatt hours per year. So approximately 2.5 times the consumption of other households have the consumption of the HSPP users. This leads to the fact that these households must have electrified their systems, but the question emerges, how did they do it? So we're jumping on to the large consumers that we found based on the survey. And as first, if you look at the electric vehicles, we see that 70% does not have any electric vehicles who have residential photovoltaic systems. 30% do, and these systems are approximately half and a half charged from one phase or three phases. I also mentioned that there is a huge amount of electrical water heaters in Hungary. However, till this survey, we did not know that what is the share specifically on these households. We concluded that approximately 58% of households have electric water heaters. However, we only know 5% of this, because 5% of these electric water heaters are on a separate metering system that are specifically with tariffs for these electric water heaters. And 35% out of this 38% are behind the meter, so these are not measured specifically and separately. And last but not least, we also had questions about heat pumps. In this context, we mentioned air conditioners that are air-to-air heat pumps and heat pumps that are air-to-water heat pumps. Basically, 70% of the owners had ACs, so air conditioners, but only 1% is what we've known specifically because they are in a separate billing system. And 11% have air-to-water heat pumps, and only some percentage we've known before the query as of the no separate meters. So the conclusion is that the households are mainly electrified with these systems. Mostly they have heat pumps, but they also have electric water heaters in a major share, and some of them have electric vehicles as well. System sizing, that was a concern I mentioned earlier. We could justify that the system sizing is basically to cover the annual demand of these households. However, this is a great concern at the moment in Hungary because these systems will be shifted from net metering to net billing systems that will heavily affect the bills of the installers. Some of the on-site utilization of these systems, I would like to just quickly show two measures. Self-consumption. Self-consumption, that is basically the share of the on-site utilized ratio of the overall PV generation across a year. And grid reliability, that's another measure. Basically, grid reliability measures how much interaction you have with the electricity grid. If it's a value above 0, then you've basically increased interaction with the electricity grid as of the intense feedbacks and withdrawal periods of the systems. Results align with the expectations. There is a self-consumption approximately 27–30% in these households, and we could also justify that by installing these large systems that cover the annual demand, you will have much more intense interaction with the grid, and basically compared to a case with no PV scenario, you will have 50% increased electricity transfer in kilowatt hours via the electricity grid. There are more details in the paper on that, I believe. Last but not least, we try to show how to improve load matching, only taking the answer of the survey, and we had several possible options. The options were, basically, I use my appliances with shifting to the sunny periods, and we found that based on the survey result, this brings an increase in self-consumption approximately 1 to 2 percentage points. Then query answers could lead to I apply automatics, and I also tend to shift my appliances. This pushes further the previous shifting to an increased 1 or 2 percentage point in self-consumption. And we could also justify that by simple electrification of the household system. So I do nothing, I don't care how the system operates. I just have more electricity consumers when I install the PV system. It actually reduces self-consumptions of such systems. Yeah, and there's an appointment to another paper. Basically, we want to use these all data to integrate into energy community simulations as well, but it's just a teaser for another paper of ours. So I guess I'm behind time, so thank you very much for the opportunity, and I'm open for your questions.
Okay, thanks a lot. Are there any questions in the room? No one? Okay, I have a quick question, or actually two. How many surveys, how many answers do you really have? Because you started in January or something like that?
Yes, it started in January and halted in January. It's quite hard, quite challenging to increase the number of fillers. Several hundreds we have at the moment.
Okay.
So it's not too much, yet we have some of the
And
results.
you're going to have it running till the end of the year, or?
At the moment, yes, we see that, but it's quite challenging finding a platform that can provide.
Okay. And I was just thinking that it will be nice to run the same survey in other places. So are you planning to share the survey, the questions, the formula?
I have not planned to put it in other places, but if you're interested, I'm open to it.
Yeah, it will
be a pleasure.
I think it will be great. So,
let's go for it.
Okay.
Thank you very much.
Thanks a lot. So next is Catherine Calatwit, I think. So we are moving now to wind, and this will be the last talk in this session. So next is lunch. Okay, so your presentation is already here?
Yeah, I'll just probably check it again.
You probably can find it better than me. Okay, let's see here. And this is the pointer. You can use the pointer. You have to be here because you have to speak to this to this microphone. This is the power. The laser. Yeah, it doesn't look too right. Okay.
Yes, so good afternoon, everyone. I'm Katrina Kalatit from ICREPQ Technologies. Today I'll be presenting our research on the development of a near-ground novel wind energy converter. We'll be looking at the challenges, potential solutions, and how do we evaluate it using the computational fluid dynamics. So the motivation here is a utility. Wind turbines have been a great success, scaling from 0.1 megawatt to 10 megawatt. We can see the standard design is the three-bladed upwind pitch control horizontal axis wind turbines. And however, these did not translate to small-scale domestic wind energy harvesting system. So we are now focusing more on the closer ground, which is much more turbulent and lower wind speed. So from the existing studies, we've compared the utility scale wind turbines and smaller scale devices. So the comparison between the two is that wind direction changes slowly enough for effective yaw control, while for smaller devices, the wind direction changes too quickly across the rotor area for effective yaw control. So there's a mismatch between the conventional wind turbines model. So the question is, how do we directly compare it, like the large scale with the smaller devices? So we thought of designing or redesigning the technology that are more suitable for the near ground wind conditions. So here's the solution for the small turbines. As we can see here, for the challenges that I mentioned earlier, the wind direction changes and the wind speed as well. And for our design, this is currently the design of our product. We have the 6 ducts in a hexagonal arrays and a nose cone and 2 airfoil inside each ducts for better flow control, as we can see here. we can channel the wind into the prime mover and use the ducts to guide the flow effectively. And then we subdivide this to capture the area using multiple small ducts movers. So this is followed by decoupling the power conversion using the accumulators. I'll go much more detail regarding the design and how it works in the next few slides. So for the design task, as we can see here are the integrated design consideration. We first look into the shroud or the duct design. We shape the shroud that can directly, the flow to directly go through the channel and have the channeling effect. We've also considered the Venturi effect in this to better make use of the available wind. And for next is the blade design. We currently use symmetrical blade design of NACA airfoils, including NACA 0012, 015, and 0018 for oscillatory motion in pitch and plunge motion. We made sure also it will reverse pitch between sweeps, as we can see here. Also, this is followed by the accumulator. We made sure also the accumulator system can handle a wide range of torques and different wind conditions and wind direction and wind speed, and while generating pressure to store useful energy. And after designing all these components as a baseline, here is a core design task now. After shaping these hexagonal arrays with 6 ducts, we've determined the optimal balance or the thrust coefficient between the airflow and the energy extraction. So we use the thrust coefficient to represent powertrain effects on airflow instead of simulating a full modeling of all the components, which is impractical, especially is much costly. So for the aim of objective, this is finding, as I mentioned earlier, is finding optimal thrust coefficients for best performance. This is the first stage. We focus more on design and performance optimization. So once we identify the best optimal thrust coefficient, we move forward to, since we identify these optimal thrust coefficient, we move forward to identifying the pitch, torque, and tip speed ratio of the airfoil. At the moment, we are focusing on the symmetrical airfoil since we have a much complex airfoil that is undergoing pitch and plunge motion, so we focus more on the simplest model of the airfoil. So after establishing all this information, we move forward on simulating the model performance in different environments, including the rural, urban, and wind farm layout. This will be in the future study. And we can also assess the wind conditions or behavior, power extraction, energy extraction in multi-arrays of full hex devices in different applications. And we also analyze interactions such as the wake interaction and nearby structures, buildings, trees, and other atmospheric boundary layers. So for our device and method, we now here have the full hex is what we call it. We have the 6-channel, including 6 ducts, and this is the description or the specification of this full hex. The total height that we can see here is 2.27 meter, and the length is around 2.29 meter, and the inlet area and the swept area of where the airflow is moving in a pitch and plunge motion. So for the method, we use the porous volume in CFD. This is a representation of the 2 airfoil in each duct to exert an inertial resistance towards the flow into the 6 ducts in the hexagonal arrays. So the task that we have done is we calibrate the inertial resistance value against different flow conditions. And also we've considered wind speed measurements in a wind tunnel for a single channel. And after that, we explore different airflow, resistance, and power extraction for a full design up in a virtual CFD wind tunnel. So this is the model of a single channel. The one I showed earlier is a full hex with 6 channels. Here we started from this model using the Fluent. We set up the inlet and outlet area from the single duct, and these two are the representation of two airfoils inside a single duct. And here's also the mesh, which has around 1.5 million mesh to have more accuracy of the results. For the full hex in virtual wind tunnel, so we place the full hex into the ground level of the full domain here, and I mentioned here the dimensions as well. This will investigate the airflow into the duct and also around the duct to assess the performance in terms of velocity, magnitude, and static pressure. So for the results, here is the case for 12 meters per second. I've only added 2 cases here. We've conducted different inertial resistance. So here is a comparison for the inertial resistance for 3 per meter and 8 per meter. So the difference between the two is that, as we can see from the 8 per meter, there is a deflection and much lesser wind speed up as compared to the first or the left side of the image for the inertial resistance of the 3 per meter. We can see the airflow moves more inside the duct as compared to the second image on the right. So we can see here the graph of the effect of the inertial resistance. This is efficiency against the inertial resistance. So we've analyzed the full hex and also at the front area of the airfoils and also at the rear set of airfoils. But for this study, we focus more as a guideline for the full hex since it captures both the inlet area, first airfoil, and the rear airfoil. So as we can see here, the efficiency is at 9%. At the peak inertial resistance is at 3 per meter. So we've showed earlier that the airfoil moves more inside the duct, which shows that this is more efficient or the optimal inertial resistance when comparing the 2 values. So for the conclusion, so after knowing all the optimal inertial resistance and also what are the effects in terms of the resistance, we were able to balance upstream and downstream of the airfoil contributions of the first and the second airfoil. And from there, we can identify the results of the airfoil design and work through the airfoil shape, pitch control, and oscillations. And moving forward, we can also simulate it in an application in terms of real environments, for instance, urban, rural, or wind farm layout. So I think that's everything. I have a poster for tomorrow as well if you're interested. Please do go there. Thank you, everyone, for listening.
Thank you. So, any questions here in the room? Anyone? Oh, there's a question over there.
case, for this first stage, we've just analyzed in a smooth flow area, which is installed in a wind tunnel, virtual wind tunnel. So we expect a non-disturbed one, but yeah, that's an important part of looking at the efficiency and performance of the full dock design. That will be in our future study, but for now, this is focusing much more on not much turbulent wind flow. Yes. We have to consider that for sure, especially in a different environments. As you mentioned, urban layout, it's much more disturbed wind flow.
Anyone else? No? Okay, I have just a very short question. So this is going to be, you're trying to make a commercial product out of this? And do you have a time frame, more or less? When do you expect to have this working? When do you have everything?
For that, I don't have the answer to that, but we are more focused on design and performance optimization. Okay. But we're hoping to have that as soon as possible once we already conduct the full simulations of every cases. Okay. But for now, this is just an open discussion of the design and performance.
Okay, that's great.
Right.
Okay, so thanks again.
Thank you.
Also thanks to all the speakers, because we have been very exactly on time. So it is lunchtime now. You just go downstairs, just go outside, and then there are some stairs. Go there, down, and then it is a corridor like the one for the posters, and you will get to the cafeteria. And I believe the lunch is there, but I am not completely sure. So it is on your own to find the food, but just follow your instincts. And we will be back at, I can't remember, but I think it is 2 hours for lunch. So we'll see you again here and also in the V1, in the V room over there. So thank you again and enjoy.
señal cuando... Okay, so can we start with the session, the first online session today? Okay, hello and good afternoon to those joining us from this time zone, and a warm welcome to everyone, wherever you may be joining us from. My name is Silvia Alonso. I'm honored to chair this first poster session, online poster session, and we have 5 papers, 5 posters in this session. Each presenter will have from 5 to 7, maximum 7 minutes to do their presentations, followed by a brief opportunity to make questions by the audience. We are going to follow the order on the program. We will start with the paper number 280 by Apple and Bocconi from the Budapest University of Technology and Economics, titled "The Impact of Renewable Energy on the Stability of Future Power Systems." Isvan Bocconi, all yours. Yours.
Thank you very much, Silvia. I guess the echo is off. So thank you for the opportunity to be the first in this session and to hold our presentation from a couple of thousands of kilometers away. I hope you have a wonderful event there. And I would like to give a short summary about the work that Veronica put together. Unfortunately, she's unavailable currently, and I had the privilege to give a short summary about her thesis and her work regarding the impact of renewable energy generation in consideration of stability of the future power system. So altogether, the main target and reason why we decided to discuss about and around this topic is quite obvious regarding the challenges and the causes on the electric power network, not only from static but from dynamic point of view as well. And therefore, we suggested to make different scenarios regarding how to implicate and involve the renewable energy generation into electric power system generation. And Veronica decided to choose 2 absolutely different environments and analyze the as-is situation and causes, and define future scenarios and what will happen if type questions. So the 2 different areas which were chosen, one is the eastern part of Germany, led by the 50 Hertz transmission system operator, and the other one is the Balear Island environment. And therefore, I already mentioned you that these 2 absolutely different environments, because in Germany part, the 50 Hertz TSO is on quite good interconnection capability, a looped network area from a geographical point of view, absolutely connected and together working area. And the renewable energy penetration, it's more than 70%, so quite high. In consideration of the Balear Island, more or less serial connections, altogether I guess only 1 interconnection, and the topology and the whole operation is quite different. And altogether the renewable energy penetration is approximately 20%, 18 was in 2024, so quite close from above the 20%. And in these 2 absolutely different areas, we made different scenarios in 2 main and 2 large groups with power system, with Dixieland Power Factory. One part was the static analysis, so load flow analysis, voltage condition analysis, short circuit simulations, and the second one was the frequency stability investigations and the dynamic simulations. Of course, each modeling necessity depends on the availability of the data and the information. So much more information was available for the static simulation, but altogether it was capable to do both dimensions. So couple of sentences about the results. As you can see, the seasonal effect. So one is winter, one is spring or summer part in different scenarios are quite different from a voltage, volume and angle point of view. So we manage the complex analysis and the complex measuring units, and not only there, but in the Balear situation as well, but quite different aspects. Regarding the different scenarios, we assumed the national energy policies and national energy plans, how the renewable integration will spread out in 5, 10, 15 years term, and make the analysis about the voltage stability conditions and the frequency stability conditions. The voltage part was much more interesting on the long run, because sure, of course, we had the appropriate data sets, but as you can see, and I previously mentioned, the different volumes of the as-is renewable volumes, and on the long run, spreading out had the different effect on both network parts. And I know that time's running, but I would like to emphasize two important parts from the whole research and analysis. So one thing was the impact of the rising consumption and renewable integration, and it was differentiated into two analyzed network model, but it still experienced larger frequency extremes on the continental side. The rate of change of frequency values were generally lower at the Balearic Island, of course. It showed greater voltage sensitivity, but it came from the topology and the built-in capacity itself. But a semi-isolated structure like this island or the Northern Ireland and the UK has the same impact and influence. The other part is the rigid systems and more prone to voltage drops and frequency instability aspects. So as the renewable share increased, the traditional frequency regulation and voltage control capabilities, I should say, from step by step disappeared. So the conclusion was that both network types required targeted upgrades, not only from network asset point of view, but from control and stability strategy point of view as well. That's from our side, and thank you for the attention. I'm waiting for the questions and comments. Thank you.
Okay, thank you very much for your presentations. I don't know if there is any question. If there isn't any question here or in the chat, I have a question for you. I'm just curious, are you planning to repeat or to expand this study to any other place, to any other network? I don't know if it is interesting for you, maybe the Canary Islands, where we are here today in this Congress, because it's an example of an isolated network. I don't know if it is possible to do this work in a region like that.
Yes, thank you for the question. We already think about that, not only because of the conference, but from other perspectives to do that analysis. Unfortunately, the data sets were not complete. Therefore, we decided to focus on those areas which are, how should I say, more covered. But yeah, the model is capable to do that analysis. And from that perspective, we plan in the near future to do one more island. This is close to Italy, in Sardinia. As far as I know, Sardinia has one interconnection, and this year they will shut down the last synchronous generator on the island. And after that, they will have only renewable-based generation. It will be a really interesting possibility from dynamic analysis point of view as well.
Thank you very much for your answer. And now, next, I would like to invite Laura Velázquez, Rubio Clemente, and Chica from Universidad de Antioquia in Colombia to present their poster titled Experimental Analysis on the Hydrodynamic Performance in 4 Configurations of Gravitational Vortex Turbines. If you are ready, I think you are connected. No, it's the people from the Universidad de Antioquia in Colombia. Connected right now. If we can go ahead with the next presentation. Laura Vázquez, Rubio Clemente y Chica de Universidad de Antioquia en Colombia. Pero no veo a ninguno de los tres conectados. Pasamos al siguiente entonces. Pasamos al siguiente entonces, ¿no? Okay, let's go ahead. We are going to the next presentation. I would like to invite Vokoni, Taxi, and Hartman from the Budapest University of Technology and Economics to present their poster number 296, titled Towards a Novel Framework for Power System Stability, Introducing System Rigidity. Please go ahead if you are ready.
Thank you again, the possibility. I'm back. This time, this paper, absolutely different one, and because it's different approach. So, a couple of years ago, our research group decided to make analysis regarding renewable energy generation from a dynamic point of view, what kind of influence and impact it can occur on the electric power network on different shares. So if we have, for example, 5% or 10% of the renewable generation, it has a dedicated impact, and of course we can handle the 100% only power electronic based generation portfolio. But what is the transient during this necessity and activity from one side and from the other side? How can we treat the renewable based energy generation, so that all kind of energy generation which comes from power electronics connection, from inertial point of view and dynamic behavior point of view. And our approach based on that topic and that analysis, and it's a more theoretical analysis from twofold, of course. One part is today, all the simulation and analysis are based that we tried to force the renewable energy generation to behave like a synchronous generator. And I'm more than sure that it won't produce a real answer or at least real solution, because those assets, those equipments are not synchronous generators. So we decided to model somehow, not from a control theory point of view, but power system network point of view, the behavior, the dynamical behavior of those energy productions. And the second hypothesis came after that point. What are the time steps, how we can analyze that? Because in consideration of synchronous generators, we can speak about from 2 to 5 periods. So, for example, 5100 milliseconds until 1, 2, 3 seconds. And these power electronics assets, these are RLC loops, are in another time dimension, another time frame. So we are talking about microseconds. And how is it possible? Okay, unmute because.
It's okay, go on, yeah.
So the
sorry.
Other aspect is how to handle from modeling and simulation point of view the different time frames, because if we are talking about a switching event on an EMC level, we can handle the microseconds topics, but those are focusing on that area and that assets, definitely what we are investigating, and not system wise. If we are talking about power system simulation analysis, we are talking about milliseconds, seconds, but not that kind of rapid changes which will occur coming from the renewable energy generation. So the question is how to combine those two different words or approaches, and how to handle on the network. And after that analysis, what we put together, we find different research methodologies to go forward with that activity, and we figured it out that if we replace the synchronous generation with renewable-based generation, the total capacity of the network can be the same. The total short-circuit power can be more or less the same, but the dynamical behavior of the network will be definitely different. And it will mean that from for a long period, any kind of perturbation coming from the network, it can hold it, it can hold it, it can hold it, and at a dedicated moment, it don't have the flexibility to react somehow to the perturbation, but it will crash and go to short circuiting, or at the end, like at the Iberian problem, to a blackout. And that's why we decided to formulate it as rigidity, and the rigidity response threshold from the network, which was derived by the Lyapunov-based analysis, and define that new factor or an index to the network. So somehow to define that rigidity response threshold, it can be a maximum deviation from system rigidity point of view, and mathematically represented, as you can see on the posters, where the system state vector is one parameter, represents the equilibrium state on the network from dynamical point of view, denotes the external disturbances, and is the permissible deviation range, which range inside the range, it can be provide the stable operation, and outside of that, no further activities. And currently, which we were not capable to put into the paper, but one analysis was quite the same regarding the results and could prove our theory, is the last summer Balkan incident from a voltage stability point of view. And we made a measurement activity at a microgrid operation here in Hungary, and from the analysis we can prove the theory, and we will provide a second paper on the real productive measurements as well. So it won't be a theory anymore; it will be a proved saying altogether. So one more sentence and I will close. Our approach introduces the system rigidity as a unified Lyapunov-based stability metric, and it was designed for a low inertia, renewable dominated power system to handle and analyze the system operation and stability on the long run in the changing environment. That's all from my side. I'm still waiting from the question and comments. Thank you.
For your very interesting presentation. I wish we knew about the system rigidity threshold when we had a recent blackout in Spain 2 months ago. Is there any question by the audience? No? I have a question again. My question is, when do you expect to have an operational live rigidity index?
If I would say a subjective or an own wish, I would say soon. But yeah, to be absolutely frank, this is a theory. We do have some measurements which can prove our theory, but there is another research running in our research lab. We tried to involve all the information from the last 3 decades, approximately more than 500 blackouts and incidents in the NSOE network, and somehow analyze the theory, how should it work, and how can we work out not only an index, but somehow to forecast the level and the possibility how it will turn out. And of course, the detailed result of the Iberian blackout can be a really good information package to fulfill the open question marks in our theory.
Thank you very much for your answer. And let me see if we have our colleagues from Colombia connected. No. So we are going to the next presentation. It's the number 302 by Taxi, Totse and Foconi from the Budapest University of Technology and Economics, with their poster Distribution Network Hosting Capacity Calculation Enhancement through Time Series Analysis and Performance Index. When you are ready with this presentation, you can share to us and begin your presentation. Thanks.
Thank you. I will just share my screen now. Let me check. My second window is shared now. Please give me a feedback if you can see it.
let me see if I... Okay. Can you please make... Oh, okay, that's what I was going to ask you. Okay, thank you.
So thank you very much. And I'm István Teci from the Budapest University of Technology and Economics. And this topic is about hosting capacity enhancement methods. So in general, the research question was that nowadays we are connecting a lot of renewables to the power grids due to the energy policy goals. And this also affects the distribution system. And usually distribution systems have a high resistance to reactance ratio, like in the Hungarian grid, with a lot of overhead lines, which are quite long. Therefore, the voltage fluctuation becomes quite regular in the hosting capacity limitation. Therefore, distribution system operators must develop their grid according to the needs. And sometimes there are shortages in the human resources and time as well. So we cannot connect infinite number of renewables to the grid. This is what brought the highlight to the innovative technologies, which could provide fast and flexible solutions to those problems. Therefore, they can contribute to the effective integration of the renewables. Our research in the beginning worked towards the framework definition of hosting capacity, which can be derived from a set of parameters that characterizes the quality of the electricity supplied by the network, such as line loading, transformer loading, voltage magnitude, and stability. And you need to collect all those possible technical limitations into one hosting capacity definition, which is sometimes quite tricky. Most of the countries use the standard EN 5160, which defines voltage quality limitations. And in our work, we proposed a new methodology, which is a performance index-based solution. And we created a grid model to analyze this kind of hosting capacity rules. So in our case, in our country, usually the so-called 2% rule is the limitation of connecting new renewables into the power grid, because the voltage fluctuation becomes too great to handle. Therefore, we analyzed a grid, which you can see here, which is quite similar to the topologies in Hungary as well. It is consisting of long overhead medium voltage lines. And our simulation method consisted of grids from medium voltage and low voltage as well. So we created a hosting capacity, which is true for one complete feeder from the substation until the end of the low voltage line, which is not usual in the practice. We usually calculate the different voltage levels separately. But in our simulation, we showed that the limitations due to the low voltage sometimes affect the medium voltage quite greatly. And during the simulation study, we used year-long load profiles, and we also integrated one innovative network element, which is a serial voltage regulator, which can be thought of like an OLTC transformer, which is not inside the substation, but instead of that, somewhere on the line where the voltage becomes problematic. And our method was that there was distributed generation around this feeder at the beginning, and we used the scaling factor to increase the cumulative power of distributed generators, and looked for the hosting capacity limits defined by the grid constraints. And here you can see what we call the scissor diagram, where you can see the voltage magnitudes along the nodes from the substation until the end point of the low voltage. And in the beginning, this figure covers the hosting capacity for the base case. And here it is the general 2% rule calculation, which is the voltage increasing capability of all the renewables. And then our hosting capacity methodology covered every aspects of voltage variation or line overloads, transformer overloads, but left out the one limitation of this 2% rule, the voltage change. And here you can see the voltage profile along the line. You can also see the border line between the medium voltage and the low voltage. And on the low voltage, there is other limitation, which is 7.5% nominal voltage change. This is a special Hungarian rule. We also have to meet that. And in general, if we just leave out the 2% voltage change, voltage fluctuation limitation, the hosting capacity can be increased by more than 5 times. And this shows that there is a real possibility between just calculating the worst cases and using time series analysis with load profiles. And here you can see the effects of 2 different network development methods. One is the innovative solution, which is the series voltage regulator. This is implemented on the network and controls the voltage at a dedicated point. Here you can see the different voltage levels by a statistical method called box plot. And here we built in the voltage regulator, and you can see that it changes the voltage profile of this feeder by decreasing the voltage and working against the voltage rise capability of the distributed generators. Beside that, here you can see the line loadings. Because the serial voltage regulators are only controlling the voltage, they doesn't really have effect on the loading conditions. And beside the innovative method, we also checked quite regular grid development method, which is a cross-section increase. So using larger cables along the grid. And here you can see the effects of the cross-section changes also by the box plot, which means that also the line loading conditions can be met in case of cross-section changes. So this is a more rigid conventional method, which can create larger capacity extensions. As you can see here, from the base case, it's 10 times increase with series voltage regulator and 15 times increase with the cross-section increase. So that is the best method. However, it is the most cost intensive to change all the lines and build all the grid. And also it creates the most customer intervention as well. So in general, that was our approach to create time series simulations where we use all the loading conditions as an input. And instead of the worst case, we use real data to model the limitations. And also we modeled the 2 grid parts, the medium voltage and the low voltage in parallel in our simulations. So these are not separated. Therefore, we think that this methodology is more accurate than the current practice of distribution system operators. Beside that, we also showed the effects of different kind of network development methodologies. One is an innovative method, which is a series voltage regulator, and the other one is a conventional method. This is basically what we did here. Thank you very much for the attention. And if you have any questions, just feel free to raise it.
Okay, thank you for your presentation. Is there any question by the audience? No, it's not a surprise that I have a question. Well, I think I'm just curious again. You have chosen a rural network for your model. What do you think that could change in terms of results of your work if you choose an urban network?
That is a great question, because the limitations are depending on the key factors of the grid. So what is the impedance, what is the line length, and all those things. And the reason behind it that we choose this was that the distribution system operator who gave us the data has a quite rural network, so they were interested in the rural networks. But beside that, the key difference is that usually in urban networks, not the voltage, but the loading is the limiting factor. Therefore, the innovative method, the series voltage regulator, wouldn't be a good solution in those cases, because it cannot help you with the loading problems. It cannot create additional current transfer capability. Instead of that, you need a new substation, or you need a cross-section increase in those cases. So this is the key difference. But yeah, the grid parameters are really important. And also, I think for further research, this is our main goal, to characterize grids and show that by different attributes, what is the most effective solutions to create hosting capacity.
Thanks for your answer. And I think we can go on with the next presentation. It's the final presentation, but I think I will want to see if the people from Colombia is there connected, but they are not connected. So we are going to proceed with the last presentation. I would like to invite Sivojevic, Eguia, Juric, Laruskain, and Torres. This is a joint work from the University of Belgrade in Serbia and the University of the Basque Country in Spain, with their poster Analysis of Phase Comparison Applications in Power Transformer Protection Against Internal Faults. If you are ready, you can share your presentation and start when you want.
Hello, everyone. My name is Jelisaveta Krstivojevic. I'm from University of Belgrade School of Electrical Engineering. And let me share my screen first. So I will start. Just a second. Can you please confirm that you see? Hello, anyone?
Now we can see it.
You
Yes.
can see it.
Yes, thanks.
Okay. The topic of my presentation is analysis of phase comparison application in power transformer protection against internal faults. The objective of this paper is to examine the possibility of applying phase comparison of primary and secondary currents for protection against internal short circuits. Directional index is used as a phase shift indicator. When currents being compared are periodic, directional index represents the cosine of the phase shift between the phase shift angle between them. And the basic idea of applying directional index in power transformer protection is that directional index is equal to 1 under normal operating conditions and during external fault, external short circuits, whereas in the case of internal faults, its values are greater or equal to -1 and less than 1. The algorithm is presented on the poster. I would highlight that after calculating the required RMS indicators and directional index, the methodology for internal fault detection is based on 2 sequential conditions. First one is an identification phase triggered by an overcurrent condition. And the second one is directional index assessment used in the fault decision phase. The methodology is tested using MATLAB Simulink generated signals where inter-turn faults affecting different percentages of transformer windings are simulated. The proposed approach is compared with conventional differential protection. And results, the first diagrams in the simulation results section refer to the case when the power transformer is positioned between two active networks. Current waveforms, RMS indicators, and the directional index can be seen for 50% inter-turn fault case. While on the right side, trip decisions using the new method and percentage differential protection algorithms are shown. The tables below show the values of directional index for different percentages of short-circuited turns. The activation times of the trip signal for both proposed algorithm and the percentage differential algorithm are also presented and expressed in the number of samples measured from the moment of the fault inception. And it can be observed that in all analyzed cases, the proposed algorithm identified the fault faster than the percentage differential protection algorithm. Next, the results for power transformer positioned between active and passive networks are presented. Here, the 132 kilovolt side in the simulation model is represented by a passive load. And the results also showed that in all analyzed cases, the proposed algorithm identified the fault faster than the percentage differential protection algorithm. And finally, as an additional variation of the proposed algorithm, the identification phase is modified to be based on the observation of the primary and secondary superimposed currents. When any of the specified conditions is met, the algorithm proceeds to the next step. And to improve protection security, the transition to the next step is allowed only after one of the conditions has been satisfied in 3 consecutive evaluations. And here also, we can see that the proposed algorithm identified the fault faster than the percentage differential protection algorithm in all analyzed cases. And I would like to conclude my presentation. The paper presents methodology for internal fault detection in power transformers based on phase comparison between primary and secondary currents using directional index. The results confirm that proposed approach can reliably detect internal faults, and the use of directional index proved to be fast, stable, and effective, making it a promising option for further development and possible integration into the protection system. And thank you for listening. I hope you found it interesting. And I wanted to say that I'm sorry I couldn't attend the conference in person, but I hope you are enjoying the live event so far.
Thank you very much for your presentation. We hope to see you in person in the next conference. Any question by the audience for our speaker? If there isn't any question, I want to make a very quick question. We have 2 minutes. So in the paper, you proposed, you state that the proposed algorithm trips the signal faster than the conventional differential protection. I wonder how much faster.
You can see from the results on the poster, it is for about several samples. It depends on percentage of short-circuited turns. I can open my poster if you want again. Maybe we can pass through that if you like.
Thank you for your answer. And we are closing this first online poster session. I want to thank all the presenters for their outstanding contributions and to the audience for your interest. And this concludes our poster session. Please feel free to continue the discussion with the speakers online and enjoy the rest of the conference. Thank you.
Sí, pero tiene unas cuantas cosas que he cambiado así. ¿Me vas a dejar? Nos ponemos aquí toda la presentación, claro.
Hay que enchufarlo.
¿O usas ese o lo colocas aquí?
Tenemos aquí el manito.
Porque yo no sé, yo lo tengo aquí. Bueno, y si no está el mío también aquí, es otra opción. Pasa que ya se acabó.
El tuyo está ahí.
El mío lo puse aquí, pero a ver si veo dónde, a ver si viene alguien de aquí. Yo creo que me lo pusieron en... Esta es la tuya, ¿no? Vale, o sea que esa ya está disponible ahí. Pero yo creo que la mía la metieron en el escritorio, pues sí, esta es la mía. ¿Te pongo aquí también la tuya, Alfredo, por si acaso?
No, voy a intentar poner esta que tiene Silvia.
Presenta la 36.
No, 26.
A 26, perdón, 26. De acuerdo. A outra vai a posta. Vai a posta, porque tedes dúas, unha vai a posta.
Sí, foi a posta.
Claro, este é que vai...
Ahora,
De acordo.
oral presentation.
26, entonces, ¿cuál se ha retirado? What of this withdrawn?
Eu vou apresentar esse. This is a presentation. Yes.
Chair. So we are going to start the session. This is the oral session A2. And we have 5 presentations, but there is a change in the program because one of the presentations is withdrawn. So in the beginning, I am going to use 5-10 minutes because we have a delay in this moment. 10 minutes to present 2 ideas about the posters we are to present on Friday, okay? About our work on superconductivity. Then we start with the order of the program, with the communication, except the number 225, which is the oral session that is withdrawn, okay? Then, to beginning, this session, permit me to introduce me and present very rapid the works we are carry on in the University of Extremadura in Badajoz, Spain, about superconductivity in the electrical power system. I think this is... I think this is disconnected. Yes. Perfect. The outline of my presentation is something like this, very rapid. Something about superconductivity and the electrical application. I am going to present you some very classical electrical applications of superconductors as cable, superconductor fault current limiter, superconductor magnetic energy storage, and a motor generator, and some example of high magnetic field application. What is a superconductor? Superconductor is a material which in normal condition is a normal material. It has resistance and its magnetic behavior is like a diamagnetic or paramagnetic material. Practically, the magnetic field inside of the material is like in air or vacuum. But if the condition change, for example, if the temperature rise, low, below certain critical temperature, Tc of the material, then they become two perfect conductor and perfect diamagnetics. This means they exhibit null resistance and expel all the magnetic field inside. These 2 characteristics are very important in the application in electrical engineering, of course, because we can use this material for any application in which the resistance and the magnetic field may be a problem. The only characteristic you have to know is that this state transit to normal state if the temperature go above the critical temperature, but if the electric current go above the critical electrical current and the magnetic field go above the critical magnetic field. In these cases, the material become to normal material with resistance and paramagnetic behavior. Okay, this is the state diagram of one of the more classical material, superconductor, which is the YBCO. YBCO is a ceramic material with exchange stoichiometry with ITO, copper, oxygen, etc. But it's known as YBCO. When the state of the material is inside this state surface, then the material is in superconducting state. And if the state is defined in a point outside this surface, then the superconductor becomes in normal conductor and lost its properties. About the application, this is the first application in the idea of electrical engineer. That is the cable, a cable that can carry current without losses because it has not resistance. The material has certain losses, not Joule losses, but certain specific losses. We know AC loss. AC losses appear in the material when the current changes, but they are very, very, very low, much lower than the resistive loss in a normal conductor. This is a cable for Nexan, ICMAF, and Tecnalia. That is a consortium to construct this cable. Really, the cable, this is important. The cable is these tapes in this surface and these tapes in this surface. The rest of the cable is a mechanical stabilization and electrical stabilization, and the place where acts the liquid nitrogen or the cooler that we need to put the superconductor at the right temperature to work. Okay, the benefits of the cable, very, very quickly, is increase the efficiency of the cable, reduce infrastructure requirement. The footprint of this cable are very, very low in compare with the normal cables. Enhance the grid stability and open the possibility of distribution in DC power, because you don't need to increase the voltage to reduce the current, but because the current don't generate losses. Another application is the superconductor fault current limiter. This is an element that is connected in series with the line which we need to protect. And when the current in the line is the rated current or a normal current, then the element is practically invisible for the line because the impedance is 0. But when the parameters make the superconductor transitions, then appears an impedance in the middle of the line that can be resistive or inductive, giving two types of superconductor fault current limiter, that is the resistive or the inductive type. There are very classical types. In our university, we are working in a hybrid inductive resistive superconductor fault current limiter, which has this aspect, and you can be in Friday in the poster, 425 Suarez. I invite you to visit these posters. The SMES is very important in this moment application because they permit to store energy, magnetic energy, or energy in the form of magnetic energy in a coil, just in a coil in short circuit. A coil short circuited, if the coil is made with a superconductor without resistance, permit the circulation of the current indefinitely and can store energy like a capacitor. Is the dual of a capacitor due to a difference of potentials, but in this case, due to the current, and the energy is 1/2 of I squared, as is known. When you need the energy storage, you only open the circuit and inject the current in the line through the corresponding converter. It's a very interesting application. We have some advantages, as a rapid energy discharge is immediately, the discharge of the energy to the line, high efficiency, longevity, practically infinity longevity, because it's just a cable, no more, no chemical element, etc. Other applications are motors and generation. The generators, this electrical rotating machine reduce the volume very much because of the characteristic of the superconductor, and other application for high magnetic field, as some applications you probably know, the maglevs, as the Shanghai maglev in Service Science 2004. The tokamak is the fusion reactor in study in this moment, confine the plasma in the superconductor toroidal coil, and application impossible without superconductor, as is the NMR equipment for diagnosis. So this is an idea you can find in the posters. Thank you for include this small presentation in this session. And now we continue with the normal program. Thank you very much for the organization, by the way. And we continue on. Thank you. So the next communication is named the progression of renewable energies in Portugal and the role of SU Electricidade as the aggregator of last resort. The presenter is João Loureiro. You have the word. Thank you very much.
Good afternoon, everyone. My name is João Loureiro. I'm here with my colleague Pedro Lourenço. He's over there. Please raise your hand, Pedro, so people can know you. We are from Portugal. We work for SU Eletricidade, and we are the authors of the paper titled "The Evolution of Renewable Energies in Portugal and the Role of SU Eletricidade as the Aggregator of Last Resort." As the title may suggest, we have two main goals for today. The first one is to review the evolution of renewable energies in Portugal, present the state-of-the-art of electricity generation in Portugal, outline the future growth prospects for renewables in Portugal, and identify associated challenges. The second goal is to offer an overview of SU Eletricidade's activity as the aggregator of last resort. As you might know, Portugal is committed to the energy transition and has been adopting the promotion of renewable energies for electricity generation. The graph shows the evolution of the installed capacity over the last 20 years. During that period, around 15 gigawatts of renewables connected to the grid, and the total installed capacity in Portugal almost duplicated. In 2005, the total installed capacity was around 14 gigawatts, and around 60% of that capacity was based on non-renewable sources, so around 40% of renewables. Over the next 10 years, we witnessed the expansion of wind power. 4 gigawatts connected to the grid, and in 2005, the total installed capacity reached 20 gigawatts. The situation has reversed, and in 2015, around 60% was based on renewables. The solar power began to emerge. We see the shy yellow slice of the graph. And the next 10 years, so the last 10 years, were marked by the ascension, the growth of solar power. Nowadays, this graph is, the end is data from the final the end of 2024. The total installed capacity was 27 gigawatts, and the mix is what you can show in the cheese, I would say. Just to notice that 20 years ago, 60% non-renewable. Today, just 20%. This in terms of installed capacity. If we look closer to each of the three main renewable technologies that we have in Portugal, hydro, wind, and solar, regarding hydro, we can notice a consistent growth over time. Okay? The last edition was in 2022. It was 1 gigawatt of hydro that connected to the grid, and this is a project that belongs to the biggest Spanish utility. Regarding wind, the wind grew fast between 2005 and 2015, 2017, but it continues to grow. Okay? With a lower rate of growth, but it continues to grow. Solar is the trend of the moment. Okay? We can observe an exponential growth of solar since, I would say, 2018, 2019. And during the last 20 years, 6 gigawatts of solar were connected to the grid. In terms of electricity generation, we also can see that the situation has changed a lot over the last 20 years. In 2005, more than 80% of the total electricity generated in Portugal was based on non-renewable sources. We are talking about coal and gas, essentially. Nowadays, in 2024, more than 90% of the total electricity generated in Portugal was renewable. Of course, this number of 2024 is well connected to the wet year we had, but if you look to the graph, you can see that you had similar levels of hydro in the past, and you didn't achieve that rate. Now, incorporation of renewables. What we can see here that the addition of wind power to the mix allow Portugal to put that share of renewables at around 50%. Okay? We see that between 2014 until 2019, the share of renewables in the electricity production was around 50%. Now, with the expansion of solar, sorry? Okay, so you can't hear me. Okay. With the growth of solar, we are pushing it forward to 60% and above. On the right side, you have a comparison between Portugal and other European Union members. This data is for the year of 2023, and Portugal ranked fourth regarding the incorporation of renewables on the electricity generation. Now the future. Despite the numbers we have seen so far, Portugal continues to aspire more. And in the national, regarding the National Energy and Climate Plan, for the horizon of 2030, Portugal aspires to reach more than 85% incorporation of renewable sources in electricity by 2030. This 85% compares to the 65% of 2024. To achieve this, more renewables must be connected to the grid. And the plan forecasts more 4 gigawatts of onshore wind, more 12 gigawatts of centralized solar, and more 3.5 gigawatts of decentralized solar compared with what we have in the end of 2024. Of course, all that amount of renewable brings challenges. Okay, we will have a system flooded with intermittent generation and lack of firm capacity. It presents challenge for those involved in the sector, such as TSOs, DSOs, and producers, and we have 3 main issues and challenges. Grid stability, reliability of electricity supply, and the effectiveness of the merit order model and marginal pricing in reflecting the real cost of electricity generation. The first goal of our presentation is accomplished, so we move to the next one. That is to offer an overview of the role of SU Eletricidade as the aggregator of last resort. As aggregator of last resort, SU Eletricidade has the responsibility to acquire electricity generated by 2 kinds of facilities. The ones that benefit from guaranteed remuneration schemes or other subsidized remuneration support regimes, and the ones that, regarding the first point, they can be renewable or not, because we also acquire electricity from cogeneration. The second kind of facilities are electricity producers with connection power below 1 megawatt who do not benefit from guaranteed remuneration schemes or other subsidized support regimes. We called it a market-based remuneration framework. Regarding the first point, it is something that we are doing for some time. We have around 26,000 units and 80,000 megawatts under management. And when I mean under management, I mean to forecast the generation, sell it in the market, and then invoice the... okay, 10 minutes already. I have 2 minutes. Okay. The most recent activity of SU Eletricidade is the market-based remuneration framework. It was assigned to SU Eletricidade more recently, and regarding this activity, we have already 4,700 units and 140 megawatts under management. We will focus the rest of the presentation on this second activity, because it's the recent one. It was assigned to SU Eletricidade in 2019. It is well connected, well linked to the growth of small-scale generation. For instance, self-consumption units that have grown very fast since 2020. The numbers are the ones that are on the right side of the presentation. In 2020, 250 megawatts connected to the grid. In 2025, 2,100 megawatts connected to the grid. This activity allows that small producers can monetize the electricity they generate, even if they don't have an offer in the liberalized market. Regarding the market-based remuneration scheme, this is the formula we use to remunerate the producers, there is a component that is connected to the electricity they inject into the grid, and it is evaluated at market price, day-ahead market price from OMIE, and two costs that the producers must pay. One is a fixed cost, and the other is related to the imbalance costs. I have to finish. Sorry. Those are the numbers of our portfolio nowadays. We have around 4,700 active contracts, 140 megawatts of capacity. We have acquired in the year 2024 to these producers around 57 gigawatt hour of electricity. Last considerations, and as I have to finish, it is what we have talked during the rest of the presentation. So Portugal, I think, is well positioned to be in the leadership regarding to the transformation of the sector to a more renewable sector, and SU Eletricidade is able to continue to help in this transformation. Thank you very much. It's my contact and previous contact.
We have time for one question.
No one wants to make questions.
No one question? I have one question. But it's very easy. It's very easy. In the graphic you use in photovoltaic and wind power, I think it's one of the beginning.
In the beginning.
Doesn't matter.
No, we will.
The wind generation is this one is playing the curve, and solar and photovoltaic is increasing very much.
Yeah.
What is the reason? Is political or?
I believe to install wind you need to have money, of course, and in the beginning it happened because there were auctions, or in Spanish we call it subastas, right? And feed-in tariffs for those generators, those investors.
Okay.
For solar, it is more related with the small producer, the one that install the panels in his own house.
And also, in Portugal, in the last years, we have a lot of options for the solar capacity. So, in Portugal, in the last years, we have a lot of auctions for the solar capacity to give the points to interconnection in the grid. This is the bad point in Portugal to installation a power plant. So these auctions happened specifically for the solar production. So in the last years it happens, and it contributes to the big growth of the solar plant. Okay.
Thank you,
Thank you very much. Okay, we thanks again the speaker.
Thank you very much.
Okay, next speaker is Diane Rodriguez dos Santos with work entitled Modeling the Synergy of Wind and Photovoltaic Power in Galicia using copula theory. Okay, thank you.
Hi, it's a pleasure to be here. My name is Diane. I'm so sorry, I don't speak English very well, okay? My paper is modeling in the synergy of wind and solar power in Galicia using cupola theory. The change to renewable energy is important. Wind and solar energy help with them, but they are not always available. When we use it together, it gets better. Galicia in Spain has a lot of wind and more sun now. We study how wind and solar work together there. We use the data from 2014 to 2024. Our goal is to help plan better energy for the future. Cupola theory is a statistical method used to study the relationship between two variables. It was credited by SALA in 1959. People use it into financial and the climate and the renewable energy. A couple can join two or more distributions into one. It is effective for identifying complex relationships, such as those in wind and solar energy. It was better the normal correlation. Cupola can work with various data types of the effectively display extreme events. This helps us understand and improve energy system. This study model depends between month, wind, and solar energy in Galicia, using cupola theory, addressing their season variable. The approach improves feeding weighable marginal distribution. Second, select the best fitting and next cupola via statistical criteria. Simulating scenarios to analyze joint behavior and complementary. This method enables a realistic assessment of how wind and solar social interact, supporting better energy planning. We study how wind and solar energy work together. We want to know the change of having a lot of little energy. This helps people want their energy using more efficient and maintain a stable electric system. In Galicia, wind energy is strong in winter. Solar energy is strong in summer. Together, they are helping maintain steady energy levels throughout the year. This system is strong and help with clean energy. The Kolmogorov-Usminov test revealed the weighable distribution provides the best fit for wind and solar generation. This is because their data is not negative and is not even. We used maximum likelihood to estimate values and employed cupola theory to model the relationship between wind and solar. The figure 3 shows this relationship between the variables in Galicia. They use A, I, C, and B ICREPQ test to select the 217 rotated BB8 cupola. It's the best model for combining with the solar data. This model shows a moderate negative relationship between them. The model excels the illustrating extreme events and how wind and solar energy can complement each other. We conducted 1,000 simulation, and is a figure 4. The results closely resemble real data, exhibiting the same essential pattern. These help us study various scenarios and plan the energy system more efficiently. The test, the model, we used B-Gulf test with the rotated BB80 degree, 217 degree cupola and 1,000 samples. The test showed not significant difference between the simulated and the real data. See, the real data, I'm sorry, I'm nervous. The regular data and the simulated, the discrepancy is a little, yeah, for two variables, wind and photovoltaic. This man or model performance will for wind and solar energy source combined also shows that the result is very close. CU table indicates the model is reliability for planning sections. For conclusion, this study employed the cupola theory to investigate the relationship between wind and solar energy in Galicia for 2014 to 2024. We found that the work went together in the different seasons. We used the Weibull distribution and the rotated BB8 cupola. The model demonstrated how wind and the solar energy change in tandem events in extreme cases. Test and picture provide the model is good. Their results facilitate energy planning and enable the prediction and integration of renewable energy sources. This method can also be applied in other settings and with different types of energy. I'm so sorry. Thank you very much.
Thank you for the first. Thank you very much. We have time for a question, or do you prefer?
For email.
For email. So we pass to the next speaker. Okay. It is my pleasure to introduce you. The next speaker is María Isabel Milanés Montero, and his work is entitled Net Zero Energy House Management with Stationary and Mobile Energy Storage Batteries.
Thank you very much. Good afternoon. My name is Maribel Milanés. I'm with the Power Electrical and Electronic Systems Research Group at the University of Extremadura, and I'm going to present the work entitled Net Zero Energy House Management with Stationary and Mobile Energy Storage Batteries. This work has been made in collaboration with the Nova University of Lisbon and researchers from the University of Extremadura. The outline of the presentation is shown in this slide. As you can see, first we are going to see the objectives of the work. Afterwards, we are going to present the topology proposed for the home, the modes of operation and the operation strategies are shown later, and finally simulation results and conclusions and future work will be presented. The objective of the work is to implement an energy management system for a net zero energy house. Net zero energy houses are conceived as houses aiming to balance the production and the consumption through energy renewable sources and also energy storage systems. So we are going to show a house equipped with PV panels on the roof, a stationary energy storage system, and also a mobile storage system by means of a battery electric vehicle. The idea is that the energy management strategy tries to minimize the house interaction with the power grid, trying the house to be self-sufficient, and in case we have extra production, inject the surplus energy back into the grid. The topology proposed for the house is shown in this slide. As you can see, we have I will try here. Okay, we have here a mixed topology which shares a common AC/DC converter and bidirectional and unidirectional DC/DC converters for the battery and for the PV panels, respectively, and also an independent off-board electric vehicle charger formed by an inverter and a DC/DC converter. The topologies we have chosen are simple, a full bridge voltage source inverter for the AC/DC converters, which are bidirectional. For the bidirectional DC/DC converters, half-bridge buck-boost converters, and for the unidirectional DC/DC converter for the PV panel, a boost converter. Some modes of operation can be identified. For example, we have here in red the possible operations between the unidirectional energy injection from the PV system to the rest of the elements. For example, it is simple to see that we have here the possibility to have PV to home, PV to battery, PV to vehicle, or PV to grid. In the same manner, if we consider the energy injection from the stationary storage systems of the house, we have also three modes of operation: battery to home, battery to vehicle, or battery to grid. From the mobile storage systems, thanks to the electric vehicle, we have also a vehicle to home, vehicle to battery, or vehicle to grid. And finally, if we need extra electricity because it is not sufficient from the PV panels or from the storage units, we can also supply, the grid can supply the house by means of these modes of operation: grid to home, grid to vehicle, or grid to battery. Taking into account these modes of operation, we have to see now the operation strategies. Central house energy manager is proposed. This element is continuously monitoring the data of the house and taking into account the production of the PV panels, the state of charge of the batteries, the prediction of demand. It sends active power set points to the battery and to the electric vehicle. We can see here the operation strategies for each element. For example, we have the reference electric vehicle battery current. It takes into account the set point, and also it take into account that the DC voltage in this part, in the DC bus, equals the reference value. And also we have here the reference current extraction for the bidirectional AC-DC-DC electric vehicle charger. We have a sinusoidal source current strategy. It means that it can absorb only positive sequence fundamental component. It means that if the voltage in the grid is distorted or is unbalanced, this converter ensures that the current demanded is perfectly sinusoidal. We have here the strategy for the PV DC-DC converter. It follows a MPPT strategy, a simple MPPT. The next one is the strategy for the bidirectional battery DC-DC converter. This strategy equals the one for the electric vehicle, but in this case we have a different set point, of course. And finally, we have here the bidirectional mixed AC-DC converter. Perhaps this is the most important strategy in this topology, because this converter is responsible of ensuring that we can have active power flow inside the house in the DC part of the installation. As you can see here, we are in the outside of the AC-DC converter, so we can, as I will show you later, an active power flow between the elements of the house in the DC installation of the house. Simulation results. Simulation test has been carried out. We have here the parameters used in the simulation test. We have used it in the MATLAB Simulink model, and the house is connected to a low voltage distribution grid, and all the converters have a switching frequency of 20 kilohertz. With these parameters, I'm going to show you 3 different scenarios to show some of the compensation capabilities we can obtain with the house. For example, in this case, we are going to prove the power flow between the elements of the DC part. At T equals 0.5, the PV is injecting 2.5 kilowatts. So, since there is no need of current in the house, the home energy manager sends an active power reference for the battery equals to the power injected by the PV panels. We can see here that there is a current in the PV panel and in the battery, but the rest of the elements in the house are null. It means that all the power flow we have in the house is in the DC installation of the house, from the PV panels to the battery. At T equals 1.05, the house demands an active power of 3 kilowatts, and the home energy management decide to use the electric vehicle battery to produce that power. That's the reason why we have here a negative sign, because the electric vehicle is not charging, but is charging. So we can see that the electric vehicle is the electric vehicle delivers the power the house is demanding. We have here the current of the electric vehicle and the current of the house, but we don't have current in the AC part of the AC-DC converter, neither in the grid. We have only interaction between the DC installations in the house and between the AC installation of the house, but without affecting upstreams of the point of common coupling. In the following scenario, we have the possibility to see that the PV and the battery inject power to the vehicle and the home. These are the active power taken into account in this balance. The home management system sends these two reference values to the elements in this case, the electric vehicle is charging. That's the reason we have a positive value in the reference. But the battery is discharging. We have a power flow where these two elements are injecting power into the AC installation of the house, but again, there is no interaction with the grid. And finally, we are going to see now the interaction with the grid. So the idea is to show an example where the PV and the vehicle inject power. The PV and the vehicle inject power into the system, and it is used to feed the load of the house, but there is a surplus. And the surplus of energy is injected into the grid. We can see here the currents of all the elements and the active power. And in this case, we have current in this part. Okay, this is the current that is injected into the grid, because when we made the active power balance, there is an extra power that it is not needed in the house. Well, the conclusions of this work are displayed in this slide. We have proposed an energy management strategy for a net zero energy house. It has been validated by simulation with a house with rooftop PV, stationary battery, and electric vehicle. We have proposed some different scenarios. In the first and second one, the power flow in the own DC and own AC installations are validated. That implies that the house is self-sufficient. And in the third scenario, there is an interaction between the house and the grid, according to the set points determined by the home energy manager. Currently, we are developing a laboratory prototype, and we are trying to expand this idea to more complex elements like a net zero energy building or net zero energy district, and also improving operation strategies. For example, not only taking into account the active power flow, but also the reactive power, or even eliminating possible harmonic currents demanded by the house. Well, I would like to finish saying thank you to the financial support we have achieved to carry out this work. And this is all. Thank you very much for your attention. And if you have any question, I can answer.
Perfect in time. So we have time for a couple of questions.
I see 4 converters between the PV panel and the car. And 2 of them are DC to AC and AC to DC, and 2 of them are DC to DC. So the idea came up to me that, in fact, the car is DC inside and PV is also DC. So shouldn't we try to find out a system to use the DC directly from the PV to a car? So many cars could be operated as and when the sun shines. So like you can heat a hot water boiler or something like that, instead of having many conversions in between. The DC-DC conversion is the highest efficiency, that's one thing. And DC-AC is something like, let's say, 10 watts per kVA loss permanently. But maybe you have also ideas in that direction, so please.
We have proposed an AC-DC and a DC-DC because we wanted to prove two types of chargers. I have said an off-board, but we can also consider an on-board AC/DC converters inside the vehicle. So, of course, as you say, if it is outside, we could use the car in the DC installation of the house, and we could put this car with a DC-DC converter to the common AC/DC. But if we use an onboard, a special onboard charger, the idea is to have an independent configuration.
Yes, one of the problems is the standard for charging cars, which is at minimum 6 amps. And if you multiply this with 2030 volts, you get 1.4 kilowatt. And especially in Belgium, in cloudy weather, often your PV is lower than that. So you use a lot the battery for something which could be directly to the car, in fact. Yeah, so one problem is the standard of the car. So where they charge at least with 6 amps, and that the minimum charging is at least 1,400 watts, where your PV is sometimes often lower, and that you need to charge 2 batteries, home batteries and back, only to satisfy some silly standard in the car.
I have not understood everything because it has echo. I don't know, but
So
we can talk later if you want.
There are regulations which are not in favor of using the car gradually. Yeah. Sorry, I will discuss afterwards.
Okay, thank you.
Okay, thank you very much. Okay, we are in the last presentation of this afternoon. I will try to read your name properly. Is Mr. Puchivan, more or less? Yes, is from the Faculty of Energy Technology University of Maribor, Slovenia, and his work is entitled Impact of the New Network Tariff System on End User of Electricity Using Green Transition Technology, a case of study for Slovenia. Mr. Puchivanik. Sorry. Thank you very much. I'm sorry.
I totally understand you. I'm a Slovene, and I also think this is a very hard language to understand. So no problem. Just to check. Okay, it works. Okay. My name is Sernej Počevalnik, and today I will present you the impact of the new network tariff system on end user of electricity utilizing green transition technologies, PV systems and battery storage systems, and this is a case study only for Slovenian example. So I'm here with my colleagues from the University of Maribor. I would like them to raise their hands to other people to see them. Okay. Oh, yes, I'm sorry. The first, just some pathetic facts we already know, and we already heard them today. With the rise of heat pumps, PV systems, electric vehicles, battery storage systems, and other general growth of consumption in also with the green transition with European Union, we need a robust, flexible, and above all, well-maintained distribution and also transmission system. And that requires a lot of money, and the money for that is collected via the network fee, which has to be paid by every consumer, by everyone who is connected to the system. Okay, just a quick look for the situation in Europe. Countries in Europe use different network fee calculation systems. They could be more power-based, for example, like in Western countries like UK, and they could be also more energy-based, for example, in Eastern countries, Bulgaria, Romania, and so on. We are somewhere in the middle. We have a combined system which consists of two components, the energy component and the power component. But however, all tariff system methodologies has to be approved by Acer to be fair enough and to be in, how to say that, good enough in terms of legislation. Okay, situation in Slovenia. We didn't have any major reforms in this thing. We had one simple system for last 34 years, I think. We had only two tariffs, low and high, and we didn't have any seasonal pricing, and also we didn't have agreed power and excessive power. This came into the game with the exception of Official Gazette of the Republic of Slovenia number 146/22. And from that we have 5 time blocks, 2 seasons, and we also have agreed and excessive power. And also the ratio between the power and energy component is getting more towards the power component. Power component is gaining more value. The methodology of the analysis, it's quite simple. We choose one average Slovenian house, which is located in the eastern part of Slovenia. It has a heat pump for heating and for domestic hot water preparation, and it is connected to the grid via three 25 ampere fuses. Okay, we get the data for every 15 minutes of the year. That means around 35,000 data points. And also we get solar radiation data from the Slovenian National Environment Agency, I think, to calculate the prediction of energy produced by our PV system. Then we also search the website of the Slovenian Energy Agency, where we find the real prices for the year 2024. We put that anything into MATLAB and get the results and graphical presentation of our results. Okay, the first scenario is the scenario without any production units and without any storage units. So we can clearly see on the graph the rise of the consumption in winter because the house uses a heat pump, and yearly consumption of that house is around 13,000 kilowatt hours, while peak demand of this house is around 8.5 kilowatts. The cost of the energy for the whole year is around 2,300 euros. And this will be the baseline for our next scenarios. We will calculate the payback and other economical parameters in comparison to this scenario. Okay, the second scenario is the scenario just with PV system and with the net metering support scheme. I think you know what net metering is. It is like that. They say, okay, 1 year, and we will calculate all the energy you produce and all the energy you consume. And if the consumed energy is bigger than produced, you will pay the difference. But if the produced energy is bigger than consumed, you won't get paid for the difference. Okay, we add a PV system with yearly production of 13,000 kilowatt hours, a bit bigger than the consumption. The nominal power of that system would be around 10.8 kilowatt, and the peak production will be somewhere at 11.5 kilowatts. Okay, the costs of electricity for the whole year for that consumer will be around 380 euros. Investment into such system is calculated to be around 12,000 euros, and if you calculate the payback, we get 6 years, which is quite good. The second scenario is the same PV system, but with other support scheme. Because net metering is no longer possible in Slovenia, our government found a new support scheme, which is called credit note. Okay, they say, we will give you certain amount of money for every kilowatt hour you put into the grid. And if we calculate the same thing again, we will get a payback of more than 10 years, which is no longer such a good investment. Okay, the third and the last scenario is the scenario with PV system and battery storage system. If we look at the graph of the power or energy taken from grid, we can see the flat line. That means that the consumer is actually self-sufficient. It doesn't take any energy from the grid. Okay, we choose the battery with a 21 kilowatt hour of capacity and with maximum discharge and charge power of something more than 20 kilowatts. With the net metering, the cost is practically just the same as with no battery, because in the net metering, actually, consumers use the grid as a battery, which is not good for the grid. Okay, if we calculate the investment and if we calculate the payback, we get around 12 years, and we can clearly see that this is not economically good. But with the credit note, the things get a bit different. We can see that our costs per year are becoming more and more smaller, around 40 euros per year, and the payback is around 10 years. For conclusion, as I said, net metering clearly favors just PV system, no need to install any battery storage system, while credit note favors PV and battery system, which are better for the grid also, because they don't put so much stress onto the grid in times of very big production and very big consumption. Okay, that will be all from my side. Maybe any questions?
Any question? We have time for question. It is a very specific study for a situation in your country, but my question is, what is your opinion about the impact in the end user?
Okay, I would try to answer that. My opinion, everyone is looking from the eyes to pay less. For me, I don't have a PV system at home, and I'm paying now less money for the electricity that I was paying before this reform. So I would say this is good. But if you ask someone who has a PV system, who invested certain amount of money into PV system, they would say, oh, it's not good, I have to pay more, I will need more time to get my money back from my investment. A complex question, I think, but I think it's the right thing, because we have to look that we need money to maintain our grid, and with the bigger and bigger stress put on our grid, it won't be easy.
Okay, there is a question.
Yeah, so I see very similarity between the Flemish grid in Belgium and Slovenian. And we moved gradually from net metering to different tariffs and to dynamic tariff. But in fact, what I see, it's always in favor of the distribution company and in disfavor of the PV owners. So we see an enormous fallback of PV and battery selling in the country because of the tariffication. But there would be a solution, and this is we see that often we get negative tariffs in dynamic tariff for sure. So this is 7,000 hours a year or something like that. But even recently we see negative tariffs averaged over a month for injection. And this is new, but it means that the benefit of having PV is only what you don't take from the grid and what you consume yourself. So, but the new challenging and new problems arise due to the tariffication system. But the new thing would be the following. So to remove taxes when energy is negative. So to have a dynamic tariff, but to suppress all taxes when the grid tariff, high voltage grid tariff is negative, so that people have really an incentive to consume when this is available. Nowadays, taxes and grid costs are so much that they make 55% of the electricity price. Nobody has an incentive to do PV batteries or to consume at the right moment for the grid. So that's what I see as a similarity, and probably where you are going to the dynamic tariff. Yeah.
I would say this new tariff system in Slovenia is maybe not so dynamic, because the agency for the energy in Slovenia say once a year, okay, this will be the tariff for the whole year, for each tariff block. For example, for, okay, from 0 to 1 a.m., the price will be like that. And from 1 a.m. to, for example, 5 a.m., oh, the price will be like that. Maybe it's not so dynamic.
No, but Europe wants to promote the dynamic tariff. But in fact, the problem is that it's not in favor of the PV owners. Yeah, that's a problem which I recognize, and which is part. You are on the way to dynamic tariff with 5 tariffs levels. So, but we have 96 tariffs, because each quarter of an hour is different. If you have a dynamic tariff. I had it for 6 months and I removed it. It was a disaster.
Very interesting, because 96 tariffs, okay. In our country, 5 tariffs.
Each day.
Ooh, even worse. In our country, we are really having trouble with people because of 5 tariffs. And we will need some time to tell them, okay, the system is a bit different now than it was, 40 years ago. And we really have problems with that. With 5 tariffs, we are having a lot of problems. This tariff system is constantly published in Slovenian newspapers. Oh, they're cheating us. They are stealing our money away. They don't upgrade our system. And this will be a problematic story, I think, for us.
I recognize the same problem. So if you only have a benefit for the grid owners, people feel contrary. So one should have a win-win situation where both parts have some benefit. In fact, that's where we have to go to, I think. But this is not true for the moment. For the moment, the grid owners can dictate a lot.
Okay.
Okay. Thank you very much, speaker. And thanks to all speakers of this session. We finished the session more or less on time. Thank you.